Okay, so today we're going to continue on with first reductive amination as a strategy to make higher order amines. And then we're going to look at two more addition reactions to oxidation state 2 functional groups, aldehydes and ketones. So one of those reactions is called the Baeyer-Villiger reaction, and that will be our transition into making oxidation state 3 carboxylic acid derivatives. Any questions before we begin? So we left off on this slide introducing reductive amination, where we saw that we can take a carbonyl, condense it with an amine to make an imine. Now with sodium cyanoborohydride in the presence of acid, so that those two things are the equivalent of H2, which reduce that double bond. So essentially the acid protonates the imine, the hydride then reduces it. So we'll skip over that mechanism so we can get to this exercise. That basically classifies the type of amine we want to make and what we need to start from. So we can make any amine 3 different ways, and we'll run through this exercise. You have a carbonyl species. Then you're reacting that with an amine. And if you start with ammonia or a primary amine, you generate imines. Or if you start with a secondary amine, you generate an enamine. So aldehyde plus ammonia will generate an imine. And then when that's reduced through reductive amination, you get a primary amine. So really the strategy is how do we make the higher order ones, the secondary and tertiary. And again, you have to analyze what's bonded to the nitrogen, whether you need to start with an aldehyde or a ketone. So aldehyde plus primary amine gives the imine, and then reducing it gives the secondary amine. So the same, again, sort of holds true with ketones as well for ammonia and primary. But now the issue was with secondary, that generates an enamine because we have to lose water. And the alkene part comes from the alpha proton. So we'll talk more about alpha carbons today as well. That's going to be important for us. And then the enamine gets reduced to a secondary amine. So again, the reductive amination, you do need acid and the hydride reducing agent, which is sort of forming H2 as an equivalent. So to put this into practice, like we saw with alcohols, you can make any alcohol 3 different ways. You can make any amine 3 different ways using reductive amination. So we'll look at this compound, N-ethyl, N-methyl cyclopentanamine. And so we see that it's a tertiary amine. And really what we're looking at is the scenarios from nitrogen to the 3 different carbon substituents. So in our mind, we're going to cleave that bond, figure out what starts from the amine, and then what gets the carbonyl component. So I've written this table out so we can see what the 3 different scenarios and the coupling partners are. So maybe I'll do these in different colors here. So we see the nitrogen. Then we see this ethyl group. So let's look at that bond disconnection first. So I want to break this bond, N to C. And I'll call that scenario 1. So to make that product through reductive amination, the part of the molecule that has the nitrogen is going to become a secondary amine. And then the other part, since that carbon has 2 hydrogen substituents, it has to come from an aldehyde. So a 2-carbon aldehyde. So if you condense those together, you're going to get an imine, or excuse me, an enamine that when treated with reductive amination conditions gives you that tertiary amine. So we'll just go clockwise around sort of the nitrogen. So now in blue, I want to make this bond. So now it's that secondary amine. And so we would need a 1-carbon aldehyde, that would be formaldehyde. Then the third scenario, we're still starting with a secondary amine. But now our carbonyl compound is going to be a ketone. So it's a pretty powerful method in the sense that, given any amine class, you can think of 3 different ways of making it. And practically speaking, if you were doing this in the lab, you would say, what are the cheapest reagents I can do this with? So that would be sort of consideration number 1, probably. Consideration number 2, in a very close second, would be any safety issues of handling these things. So for example, the second case using formaldehyde, formaldehyde can be kind of a pain in the butt to work with, so you might want to avoid that. The first scenario, this amine here might not be commercially available, so you might even have to make that from reductive amination. So, any amine you can make using this process. For the purposes of our class, it's just sort of a thought experiment. What are the ways of doing it? And then practically speaking, there's many issues involved in that. Any questions on that? Because I think we're going to switch gears. One more question. So we have this difunctional compound. We have a primary amine and an aldehyde. And we're going to treat it under reductive amination conditions. And the question is, what is the product? So A is the correct product. So we know that the amine has to condense with the aldehyde. So if we number we have that lone pair on the nitrogen. Let's number that as position 1, because that's going to be a nucleophile that attacks the carbonyl. So that gets us the ring size. So 6 carbon ring, or 6 atom ring. C is the imine intermediate. In the reaction itself, this would get protonated, and then the H minus would attack that carbon. So remember, the protonated imine is called an iminium ion, and then that gets reduced down to the CN sigma bond. B is not a good choice because we have a carbon there that's at a higher oxidation state. And then D is really something we haven't seen too much of, so that should just be a red flag as you're evaluating these responses. So the take-home message of this is if you have the nucleophilic component, which is the amine, and then the electrophilic component, the aldehyde or the ketone, linked together, you're going to end up with a ring. And so this numbering helps you determine what the ring size is. Any questions? Okay, so now we're going to look at, we'll spend the rest of about an hour or so looking at just 2 reactions. So the first is called the Wittig reaction, and then the second is called the Baeyer-Villiger reaction. Mechanistically, we're still adding a nucleophile to an oxidation state 2 functional group. So again, aldehyde or ketone, that's what we're starting with. Then we're going to look at how these reagents affect the formation of different functional groups. So the first one, as I said, is called the Wittig reaction. So Wittig won a Nobel Prize with Brown in 1979. So Herbert Brown, H.C. Brown, was at Purdue. He worked on hydroboration oxidation, which we saw in Organic 1. So the Wittig reaction is essentially going to take an aldehyde or a ketone and turn it into an alkene. That's the overall sort of words for the functional groups. The Wittig reagent is prepared in 2 steps. The first step generates something called a phosphonium salt. So in our periodic table, phosphorus is under nitrogen. So we've seen that when nitrogen has 4 substituents, it becomes positively charged, and it's called ammonium salt. So when phosphorus has 4 things, it's called phosphonium salt. And those are made, the classic Wittig reaction uses this reagent, triphenylphosphine. So it's a phosphorus with 3 benzene rings attached to it. So just like with nitrogen, phosphorus has a lone pair of electrons. So that's going to be a nucleophile. So nucleophile is going to react with an electrophile. In this case, we'll use bromomethane. So we know bromine has 3 lone pairs. It's delta minus. The carbon's delta plus. So the lone pair is attracted to the carbon. It'll do a SN2 reaction. So it attacks carbon, and then the bromine leaves. So now you have a phosphorus carbon bond. Phosphorus is plus, and then the negative is balanced by the bromide anion. So that overall, that's a salt. Now, the consequence of doing this, so we know that carbon is sp3 hybridized. So it's alkane-like, and it's a pretty weak acid. But you have a plus charge now next to it. And overall, that makes the CH bonds a little bit more acidic, so you can deprotonate them. So now that we've formed that salt, we're going to treat it with a strong base and do an acid-base reaction to put a negative charge on the carbon. So if we take our salt, and then the base, typically you have to use a pretty strong base, so N-butyl lithium. So I'll draw those H's out. The base will abstract one of them. So you get two other things that form beside the product we want. We get lithium bromide and then butane gas. So now we have a negative charge on carbon and a positive charge on phosphorus. This type of reagent has a special name. It's called an ylide. We'll see examples of molecules that have a plus and minus charge, like within the same molecule. Like overall, they're called Zwitter ions. Like when we get to amino acids and look at acid-base chemistry, we'll talk about charge location. Zwitter ion is a pretty broad term, but ylide is specifically related to this, where the minus and the plus are right next to each other. So that's a carbon nucleophile. And so what we've seen so far in Module 2 is nucleophiles attacking the carbonyl carbon. So that's what we're going to do. So there's our Wittig reagent. Or ylide. So let's react that with the ketone that's shown. So 2-pentanone. And what you see in the products, we have an alkene, and then we have this byproduct called triphenylphosphine oxide. So what's happening is, see this carbon has 2 hydrogens? That carbon becomes this carbon right here. This oxygen gets bonded to the phosphorus and ends up right there. So another way, another word that can be used to describe this is metathesis. So you're sort of switching atoms from one reagent to the other. So it says, can you think about the mechanism? We'll draw that on the next slide. But to kick us off, that's negative. Need to undo that. The carbonyl carbon is delta positive, the carbonyl oxygen is delta minus. So the ylide reagent, which is negative, is attracted to the positive. So that's going to attack. We form a carbon-carbon bond. And then what do we do after? How do we get rid of that oxygen?
The pi bond breaks to negative oxygen.
So yeah, we're going to have the pi bond break. Oxygen gets negative.
That's the positive.
And then it's going to attack the positive phosphorus. I'm not going to go too much into the weeds on this mechanism. It can get pretty complicated, so we'll keep the arrows pretty straightforward. So triphenylphosphine oxide is just abbreviated TPPO. So we'll go ahead and start. I'm going to just draw these sort of things stepwise. Your book may present it more of in a concerted or synchronous fashion, but to understand overall, we'll do it stepwise. So this negative charge attacks the carbonyl carbon. So now we have negative oxygen, positive phosphorus. Oxygen will attack phosphorus. So if we count the atoms, it's 4. So notice the charges now go away. So at this point, phosphorus has 5 things bonded to it. So it's now become neutral. It's allowed to do that because it's in the 3rd period of the periodic table and it has these other orbitals it can access. So what do we need to do now? We need to get rid of that PO bond and then form the carbon-carbon double bond. So I'm going to draw 2 arrows in the box. I'm going to draw one like that and then the other like that. So that forms the carbon-carbon double bond, and then it ejects out the triphenylphosphine oxide. So a resonance form for TPPO is where you're actually showing the PO double bond, and then you don't have those formal charges. So again, that carbon atom is what was delivered by the Wittig reagent. So now we've made an alkene, and so to make the connection, everything you learned from Organic 1, what are the reactions of alkenes? And we're expanding the mind map of our reaction toolbox, our strategy here. And then really the take-home message is anytime you see an alkene, you can make it from a carbonyl compound and a Wittig reagent. So you're essentially looking at the alkene and slicing it in half. One goes to the carbonyl, the other goes to the Wittig reagent. So that's the sort of classical form of it. There are many variants of this. After this was published, people started investigating it. One of the main issues with this reaction is the production of this byproduct. So a pH means phenyl or a benzene ring. So there's 3 of them. So that's 18 carbon atoms. And then what? 15 hydrogens, a phosphorus, and an oxygen. Triphenylphosphine oxide it's a white solid. It's not soluble in a whole lot, but it's a byproduct with a lot of mass. And if you're doing this on a large scale, you do not want to be producing a literal mountain of a byproduct that you can't get rid of. So people make variations of these Wittig reagents that have less atoms in it, and the term is called atom economy. So the stuff you chuck into the reaction, is it all being incorporated into the product, or is it going into some waste thing which is going to cost more money to dispose of? So in consideration of this strategy here, we have an oxidation state 2 compound, this ketone, so oxidation state 2. And we want to make this alkene. And the question is, what halide should we treat with triphenylphosphine to generate the Wittig reaction to do this? So as I said, if we slice there, we see that the ring is the common pattern, so that came from oxidation state 2. So everything on the other side has to come from the Wittig reagent. So what reagent should we use to make that? I heard 2-bromobutane. What?
2-iodopropane.
2-iodopropane. So why are we choosing that?
Because it's propane.
Because we have 3 carbons, 1, 2, 3. And then the attachment point is at carbon 2. So this is 2-iodopropane plus triphenylphosphine. That generates the phosphonium salt, and then we can then deprotonate that H to make the ylide. So as a strategy, really what you're doing is, identifying, how you want to split the alkene, what becomes the carbonyl, what comes from the Wittig reagent. So I have on here also, I just wrote in before class, the alternative method. So we'll switch the other carbon around to be the carbonyl carbon. So that could then come from this ketone, and then that secondary bromide. And again, practically speaking, the choice would be, what are the costs of these things? And I think it for Wittig. Any questions on the Wittig?
The reaction of the alternative method.
What is?
The reaction name.
This is going to be another Wittig. It's just the opposite coupling partners. That's going to.
What is the name?
So the next reaction we're going to study is called the Baeyer-Villiger. So it's going to take an oxidation state 2, so an aldehyde or a ketone, up an oxidation state to 3. And so that will then allow us to transition into the chemistry of those compounds. Before we get into that, though, we need to talk about the alpha carbon. So it's important for the Baeyer-Villiger, but it's also important for Module 4, because there's an entire chapter devoted on that. So as we see highlighted in red here, the alpha carbon is defined as the one right next door to the carbonyl group. So we know there's a lot of functional groups with carbonyl. And then depending on what R1 is, if R1 is H, that's an aldehyde. If it's carbon, it's a ketone, or if it's some other heteroatom, you're now up an oxidation state. And then the pKs vary a little bit depending on resonance and induction and those things. The sort of take-home point on this slide is, normally for an sp3 hybridized carbon H bond, the pK is 45, but once the carbonyl is next to it, it's dropping it quite a bit from 20 to 25. So there's increased acidity. So we'll circle back to the acidity part more on Module 4. Essentially what we're doing, you see that H with the blue highlight. In Module 4, all we're doing is substituting it. We're going to take H to something else. But for the Baeyer-Villiger, we need to know the subtle differences of alpha carbons. Question?
For aldehyde, is the aldehyde hydrogen still more acidic than the alpha carbon hydrogen?
This CH bond,
Yeah.
that's not very acidic at all.
Oh, okay. So the alpha carbon is.
It's more acidic, yep. So this slide is showing you functional groups that only have one alpha carbon. So again, if you look at what's bonded to the carbonyl, well, aldehydes or anhydride's a little bit weird case, but I've circled in red, those are not carbons. So those functional groups only have the one alpha position. The anhydride is kind of weird because by its definition, it's linked by a central oxygen, but you do have two alpha carbons. So it's kind of its own unique case. So the thing you have to pay the most attention to are ketones. So there's two types of ketones. I put that red line in there to show you that there are symmetric ketones. So starting from the carbonyl, going out left or right, if those side chains are the exact same, those are symmetric compounds. And really what that's telling you is both alpha carbons are the same. The non-symmetric ones, I've designated alpha and alpha prime. So at the carbonyl, you go to the left, you go to the right. If the chains or the substituents are different, then they're non-symmetric. So of the non-symmetric, we can branch off a little bit further. So if we consider this compound 2-butanone, we have an alpha carbon, a methyl group that has 3 hydrogens. Then we have alpha prime, a methylene group, that's 2. I've just highlighted one of each type. So I'm going to draw like a dashed line here. So in 2-butanone, there's 2 types of alpha carbons that have CH bonds. On the right side of that dotted line, if you look at between alpha and alpha prime, so alpha and alpha, those no longer have hydrogens. Only the alpha prime side does. So these classifications are important because, again, it's once you sort of figure out that, it's telling you exactly where a reaction can happen. So we'll revisit this again in Module 4, but we need to know some basic understandings for the Baeyer-Villiger. So let's look at, so there's cyclohexanone. So 2-methyl-cyclohexanone. How many total alpha hydrogens does it have? 3. So that one has 2, and then this one has 1. So the ratio of those is 2 to 1. So in terms of classifying them, a CH2 group is called methylene, and a CH group is called methine. So this would be choice B. Any questions now that we're sort of calibrated? So as I said, the second reaction we're going to learn is called the Baeyer-Villiger reaction. So again, we're only dealing with aldehydes and ketones, so oxidation state 2. And we're going to treat that with MCPBA. So meta, chloro, peroxy, benzoic acid. We've seen that reagent before in Organic Chemistry 1, where it can take an alkene and make an epoxide. So of the alkene, both carbons are going to form a sigma bond to the oxygen. So now we have a different type of double bond. We have a carbonyl group. And as you can see, this light blue oxygen, it ends up there. This light blue hydrogen ends up there. So the aldehyde we're starting with, propanol or propionaldehyde, oxidation state 2. The carbonyl carbon gets oxidized to 3, and now we formed a carboxylic acid. So this light blue oxygen of MCPBA is in this sense, it's nucleophilic. That oxygen has to attack that carbon. We can see that bond forming. See the aldehyde hydrogen? It ends up right there. So essentially, this oxygen is inserting into that bond. Then the blue hydrogen ends up in the byproduct on the red oxygen, right there. So overall, that's what's happening, and then we'll see how does that happen.
So the hydrogen from there stays in the acid.
So yeah, this blue hydrogen stays in the
MCDP.
MCPBA. So again, the P stands for peroxy. That's this OO bond. So it's a peroxy acid, and this is just a regular acid. So let me copy everything down here. So I'm not going to sort of color any of the atoms other than they'll all be red on this, but we'll sort of see how they move. I don't want to draw myself into a corner here. Let me think for a minute. Okay, I'm gonna go with it. If I F it up, then you'll have grace on me, and I'll retract my statement. So the first thing I want to do is protonate that carbonyl oxygen. So this is where I'm debating about. So we have MCPBA, which is a peroxy acid. I'm going to protonate first. So we've seen that before with these acidic conditions, like forming acetals or imines. We protonate the carbonyl oxygen, and the nucleophile adds. So we've protonated carbonyl, then we have this peroxy anion, and then this can attack that. That's going to form something that looks like an acetal at this point, because we have two sigma bonds to oxygen. So remember I said that the aldehyde H is retained in the original molecule. But we need to break this bond somehow, right? Because we got to get it onto that oxygen. So the driving force for this, that's going to collapse back down. That reforms the carbonyl. And then we have to break a bond. So the bond that we're going to break is that CH bond. So this is going to migrate over. And the OO bond is already weak to begin with. When you have two heteroatoms bonded together, it's pretty weak. So when we do that, we can then push those electrons onto that other oxygen. So that leaves as the carboxylate, which will abstract that hydrogen and now get us to the acid we desire, and then the byproduct acid. So the reason I waffled on the mechanism, I think for learning this, that's fine, but there's probably some other subtleties involved that I probably just don't want to talk about because it can get a little confusing. So the important step that I want to highlight is really right here. When this collapses, that reforms the carbonyl. It's this migration. You're breaking that bond. So when this comes down, you have double bond, single bond to oxygen. This is coming down, and then that's cleaving. An aldehyde will always do this. Aldehyde plus MCPBA gives you the acid. The tricky part now are the ketones, because you have carbon and carbon. If the molecule is not symmetric, which group migrates? So imagine, you have carbon, carbon. If it's symmetric, it doesn't matter, because you're going to end up with the same product, which is going to be an ester. But if they're different, then you have to decide which group is going to migrate. So aldehydes always form carboxylic acids. Again, we've now moved up an oxidation state. A ketone will always form an ester. But the subtlety then comes into when you have these non-symmetric ketones. Symmetric ketones, since both alpha carbons are equivalent, you can only produce one type of ester. Non-symmetric ketones, the alpha carbons have to be ranked. And so that's why we looked at the hydrogen count, so we can classify them. Once you classify it, you just look at a trend. Where does that alpha carbon lie on the trend? Which one is going to move faster? And so that will help you correctly predict what the product's going to be. So we'll start with a symmetric ketone. So symmetric ketone, MCPBA, we're getting an ester. And what I want to highlight, so that carbon is at oxidation state 2. It ends up as 3 in the product. So now we're in these new functional groups. This carbon, which is 0, now becomes like an alcohol. It's at oxidation state 1. So again, a symmetric ketone, you have the carbonyl, you go out, the right side and the left side are the same. So it doesn't matter if you're inserting between that carbonyl alpha carbon or this one, you get the same product no matter what. The mechanism will be the same. So we'll protonate the carbonyl, we have that peroxy anion add, and then instead of having hydrogen migrate, it's a carbon group that migrates over. So this question is asking us about the uniqueness sets. So the ketone, how many unique carbons does the ketone have? 4. And then the ester, how many unique carbons does that have? 7. So one of the things that I'm interested in my job outside of teaching here at USM as I do research, if you think about those numbers in a different way. So overall this has 7 carbon atoms, but only 4 are unique. So if you draw a line right here, there's symmetry. This reaction, when you run it, it breaks that symmetry because now all 7 carbon atoms are unique. So that sort of class of reactions, like breaking symmetry, is pretty interesting. If there's other factors involved, if the molecules are slightly different, you can do this in an enantiomeric fashion. And that's, ultimately in the big picture of organic chemistry and biology, the molecules inside our bodies have chirality. So there's R's and S's to things, right? But why is that? Like whether you believe in religion or evolution, we've to the point where, DNA has a certain chirality to it. So that double helix, it twists a certain way. Like, why is that? Why doesn't it twist the other way? So those are questions that university researchers think about and try to answer, how did it become that way? So symmetry breaking reactions overall are pretty neat. So the symmetric ones, again, you're going to get the same ester no matter which side migrates. But for non-symmetric, so we had, I think this one as an example. So that's non-symmetric. We have the carbonyl, then we have a methyl group, and then an ethyl group. So if we just game out, what are the 2 possible products? How do we then rationally predict which one it's going to be? Because we have alpha and alpha prime. So again, I didn't investigate this reaction. It's been known for a very long time. I would say that the person, when they were in lab doing this, Speyer and Villiger, were like, hey, let's try out a bunch of different ketones, see what we get. Then they looked at the results and saw that the trend that you see is what they observed. So when you're looking at the alpha carbons, the trend follows. So the H is for aldehyde. So aldehyde always gives you an acid. But now when you're with ketones and you look at the substitution patterns of the alpha carbons, a tertiary carbon migrates faster than secondary. So this sign, do you know what that's called? I think it's called a tilde. Like it's approximately the same as an aromatic group. So secondary and aromatic migrate faster than primary, which migrate faster than methyl. So if you look at this compound butanone, what do you think the product would be based on that trend? So B should be the product because it's more substituted. You have methyl. So this is kind of different. When I look at that, I call that on this trend, I'm calling that carbon primary. Because both alpha carbons are sharing the carbonyl. So this would be methyl. That carbon only has one other attachment. So in terms of this trend, I'm going to call it primary. So primary is faster than methyl, so B should be the product. So a lot of organic chemistry is really just recognizing patterns. So when we look at this ketone now, we can see we have an alpha and alpha prime. Keeping in mind that they're both sharing the carbonyl carbon, and we're not going to sort of count that in terms of the classifications. What would you call alpha? What class?
Secondary.
So secondary, and then alpha prime would be tertiary. And so we would get choice A for that. And so once we rank them, we saw that tertiary reacts faster than secondary. So the oxygen should insert right there. And so what is, based on that, what's the correct product? So we would get A. So again, we've gone up in oxidation state to 3 there, and then 1 there. So D is what happens when the other side moves. B is, as we say in Wisconsin, this is bunk. So that means it's a derailer. And so it should set off a red flag in your mind that the oxygen looks weird because it has too many bonds. And then C is just bonkers as well because we're now missing a methyl group, and then we have this weird alcohol in there. So again, as you study for the final, keep in mind that some of the responses are just, they chemically do not make sense. So here's the summary of the migratory aptitude. Again, those were the ketone cases. That was aldehyde. So you examine your structure, you classify the alpha carbons, look at this rank, and then you can see where the oxygen's inserting. So what if we consider, I'm going to draw this kind of crappily. So you have a cyclic ketone plus MCPBA. And so what that's going to do is it's forming an ester because now we're at oxidation state 3, so that's an ester. But it's a cyclic ester, and those are called lactones. So the key word here is expand. you have ring. So that's some n number of atoms. And then you have ring, and then this is n plus 1. Because now that oxygen is in that ring. So it says, what is the ring size of the product when you start with cyclobutanone? What is that? So again, it's a symmetric ketone. It doesn't matter which side migrates, but when it does, basically the thing is the alpha carbons are linked together by that carbon. So you're inserting another atom and the ring size has to grow. So I think it's on a couple slides for now, but again, there's an alpha carbon. This is beta, and then that's gamma. That's typically how these things will be referred to. So that would be called a gamma lactone. So that Greek letter implies the ring size, and then lactone is the cyclic ester. I don't know if I want to show that. It's just same sort of thing we already did. So I do want to show one more mechanism today. So there's the summary of it. The 4-membered ring, so 4 going up to 5. So as a review, we have the carbonyl carbon, alpha, beta, and gamma. What chemical shift do you think each carbon atom would have? Can you eliminate 2 choices based on just the carbonyl column? So we can eliminate A and D. So that's sp2 hybridized. So it has to be above 170. So 170 to 220, those were the carbonyl carbons. So we're at B and C. So if we look at the remaining responses, see these are the same. So that's telling you that that has to be at 68. This was 173. So now it's between the alpha and beta carbons. So yeah, B would be the best choice here. So that alpha carbon, it's bonded to a carbonyl, and so that is going to shift it a little bit further than the B carbon. And so that was stuff from Organic 1 when we talked about additivities. Carbon you're interested in, what is it bonded to, and how does it move it more to the left away from 0? So this is a carbon NMR of a lactone product. when blank is treated with MCPBA. So, huh? You said B? How many signals do you see? You see 6 carbons. So you have to start with this, because the ring is getting expanded, right? There's 7 atoms total, but 1 is oxygen. You don't see the oxygen in the carbon NMR. So you're starting with the cyclohexanone, it gets expanded into 7. Does that make sense? Tricky, yes. So again, that highlights the symmetry breaking again, because if you're starting with this, that has symmetry. You do the expansion, and then you end up with the 6 unique carbons. So now that I realize that I did tell a blatant lie at the beginning of lecture. I said we're going to learn 2 reactions. It's actually 3. The third one is kind of related to the Baeyer-Villiger, but it is its own named reaction. We probably won't have time to go into it because the mechanism's a little long, but I do just want to finish up sort of the nomenclature part of this so we know we're calibrated on these oxidation state 3 functional groups. So we've seen aldehydes and ketones. Now we're up into these other ones where there's more of them. So there's our carbonyl group. If X is a heteroatom, so oxygen, nitrogen, or halogen, that changes to 3. So you can just call that heteroatom, but all of this part to the left, that's typically called an acyl group. So ACYL. And the chemistry that we're going to focus on in the remainder of this module, so acid halides, anhydrides, again, those are the ones with the double carbonyl. Esters, amides. A nitrile does not have a carbonyl group, but it's still oxidation state 3. And we already saw from before, you can hydrolyze that into a carboxylic acid. So let me just, this is going to be the last slide, because I don't want to, the next mechanism is going to take a little bit to explain. So a cyclic ester is called a lactone. A cyclic amide is called a lactam. So a lactone, there's this oxygen and then carbon. So you name it sort of depending on the number of carbons in the ring. So gamma or delta lactone, whatever that ring size is. Lactams, by definition, have to be either secondary or tertiary, because the nitrogen already has a bond to the carbonyl carbon, and then another bond that keeps it in the ring. So if R3 is H, then it's secondary. If it's carbon, then it's tertiary. So remember, lactones and lactams are cyclic. You've probably heard of beta lactams, maybe. So beta lactams are typically found in antibiotics. And given the population of the class, one or two of you is allergic to those type of antibiotics. That's just how like genetics work. So we also saw these like sulfonamide antibiotics. People are allergic to those. It just happens. So on next class, we're going to see how we make those. See where we're at. Okay, so yeah, using this other reaction, which is called a Beckmann rearrangement. You're still doing the same kind of stuff, a condensation, and then as we saw with Bayer vinegar, a rearrangement occurs. But these make lactams. So we'll stop here for today because this mechanism is a bit trickier to think about, and then we'll pick that up on Monday.